Module 4, Energy Transformations in Matter. This presentation is developed based from the following references. So, if you want to know more about this topic, you may consult the following. The objectives of this module are to state the first law of thermodynamics and define thermodynamic properties such as work, heat, and internal energy, and to apply the first law of thermodynamics in understanding that the change in internal energy represented as delta E of a system appears as the total heat and or work transferred to or from its surroundings. Recall, in the last lecture video, we defined thermodynamics as a scientific study of the interconversion of heat and other kinds of energy. It has a great impact on the behavior of matter and energy. We will begin our analysis of thermodynamics with its laws. Just like Newton's law of motion, there is a first, second, and third law. In this module, we will only be dealing with the first one. The basis of the first law of thermodynamics is the law of conservation of energy. That is why it can sometimes be used interchangeably. Can you remember the statement of the law of conservation of energy? The law of conservation of energy states that energy cannot be created or destroyed. It can, however, be transferred from one location to another and be converted to and from other forms of energy. Wait, what? For example, in this scenario where we pick the water inside as our system, the water absorbs thermal energy from the metal pot. This is because the pot conducts the energy from the chemical energy given off by the combustion of the fuel, which is represented by the flame. To explain further the concept of the first law of thermodynamics in terms of the thermodynamic properties, let us first explore the concept of energy. For example, you have a kettle with water at room temperature, say 24 degrees Celsius. Then, we pick water as our system, and so the things other than it is our surroundings, like the kettle, the stove if there is, and the air. Water, or H2O molecules, are formed by putting together two atoms of hydrogen and one atom of oxygen, known as bond, specifically covalent bond, or in terms of thermodynamics are called bonding or binding energy of the atoms. These energies are actually potential energies that are stored and can be used later. Moreover, at microscopic level, the water molecules will have rotational, vibrational, and translational movements altogether called as the kinetic energy. This potential and kinetic energy combined together is known as the internal energy of the system or water, denoted as E, and now with a subscript 1 to signify that it is the initial internal energy of the water. Thus, internal energy can be defined as the sum of all microscopic forms of energy of a system. Then, you add heat to the system using the flame from the stovetop. Heat is the energy transferred between a system and its surroundings as a result of a difference in their temperatures. The transfer is always from the hotter body to the colder body. So, it's not what really happens as we usually say, "Hey, close the door, the cool air from the aircon will go out of the room." That is not true because the warm air from the outside actually enters the cold room. Moreover, heat, unlike other energies, is not an energy transferred by a large macroscopic force. When heat is involved, the molecules vibrate, but we can see them, can we? Therefore, it really is not an energy transferred by a large macroscopic force. As we continue to supply heat to the system, water will reach its boiling point and will start to evaporate to steam. As an effect, the molecules of the steam will vibrate or move vigorously, which leads to increase in the velocity of the molecules, consequently the kinetic energy, and so its internal energy. At this point, the internal energy can be denoted as E2, or the final internal energy. As the water continues to increase its amount in a vapor phase, its volume in gaseous phase also increases. Moreover, the pressure builds up. To release this, the steam makes its way out from the hole in the spout of the kettle, which creates a force that opens the lid of the spout and produces a whistle, signaling that your precious tea or coffee is ready to be served any moment. At this point, work was done. Work is the energy transferred as a result of macroscopic forces. It is the energy transferred when an object is moved. Unlike heat, work is macroscopic, and its transfer causes something perceived by our senses, usually the eyes and ears. In this case, the opening of the spout lid and the whistling are caused by the work done by the expanding and escaping steam. This example is a representation of an open system because mass is transferred from the system to the surroundings as the steam goes out. To accomplish our aim, which is to describe the first law of thermodynamics in terms of the heat, work, and internal energy, instead of an open system, as discussed earlier, we will relate these thermodynamic properties in a closed system. A closed system, as defined in the previous module, does not allow exchange of mass with the surroundings, only energies. This is done because the analysis of the first law in a closed system is a lot simpler. We will extract the first law of thermodynamics in a steam locomotive. A steam locomotive is a type of railway locomotive that produces its pulling power through a steam engine. A steam engine is a heat engine that performs mechanical work using steam as its working fluid. In this analysis, we set water as our system. These locomotives are fueled by burning combustible material, usually coal, wood, or oil. The combustion process releases a large amount of heat, which is used to increase the temperature of water in the boiler, converting it to steam. Then, the steam enters a cylinder equipped with piston. Here, the steam applies pressure to the piston as it expands while heated, which, in turn, moves the wheels of the locomotive. To summarize, in a steam engine, where the system is water, heat absorbed by water is an energy transformed from chemical energy. Then, as the steam expands, it does work to the piston as mechanical energy. After undergoing this process, where there are associated heat and work, the system's internal energy could now be different. To account whether the system increased, decreased, or retained its energy, this quantity is best represented as the change in internal energy, denoted as delta E. Thus, mathematically, the change in internal energy of a system, whether increased, decreased, or retained, could be determined by accounting for the sum of the heat absorbed or released and the work done by or done on the system. We can therefore restate the first law of thermodynamics as the total change in a system's internal energy is the sum of the energy transferred as heat and or work. Since both heat and work are path functions, we need to know the transition of a system in its pathway. Did it absorb or release heat? Did it do work or is the work done on it? To do this, we need to establish a sign convention. If heat is gained by the system, it is positive. While if it is lost by the system, it is negative. For work, if the work is done on the system, it is positive. And if the work is done by the system, it is negative. Moreover, if the delta E of the system is positive, the system increased its energy. And if negative, it decreased its energy. In case of the steam engine presented, the amount of heat is 4.18 joules and work is 2 joules, we are tasked to calculate the change in internal energy of the system, which is water. Delta E can be calculated by getting the sum of the heat and work. Therefore, delta E is 4.18 joules plus 2 joules. But do not forget the sign convention. Since heat was absorbed by water, 4.18 joules is positive. While work was done by water or steam to the surroundings, which is the piston, then work is negative. Then we would get positive 2.18 joules. Positive delta E means energy in the system is increased. Moreover, the first law of thermodynamics can be stated as the energy of the system plus the energy of the surroundings remains constant. Energy is conserved. Mathematically, that is, delta E of the system plus delta E of the surroundings is equal to 0, or the amount of the heat and or work of the system is equal in magnitude but opposite in sign of that of the surroundings or vice versa. For example, in the steam engine, if the steam does negative 2 joules of work, then that means the surroundings has a work being done on it as positive 2 joules. Similarly, if the heat absorbed by water is positive 4.18 joules, then the heat released by the combustion of fuel is also 4.18 joules but negative. So, from the equation above, if there is no work involved or W is equal to 0, the equation resolves to Q system plus Q surroundings equals 0, which I think you are all familiar already, or Q lost plus Q gain is equal to 0. Or, as stated earlier, Q gained by 1 is equal to the same magnitude of heat lost by the other but opposite in sign, therefore negative. When we relate the interacting system and surroundings, there will come a time they will reach thermal equilibrium. Normally, when two objects are placed in contact, heat is transferred from one to the other until they reach the same temperature, or are said to be in thermal equilibrium. When the objects are at the same temperature, there is no heat transfer or heat flow because the driving force of heat is the difference in temperature. Thermal equilibrium is the basis to another fundamental law of thermodynamics, the zeroth law of thermodynamics. This law is the basic and fundamental law that was added to the existing laws. Because it's basic, instead of having it as the fourth law, it is dubbed as the zeroth law. This law deals with the thermal equilibrium and states that if two systems are in thermal equilibrium with a third system, then those two are in thermal equilibrium with each other. In other words, if body 1 is in thermal equilibrium with body 2, which is in thermal equilibrium with body 3, 1 and 3 are also in equilibrium. To be more specific, here are the applications of thermal equilibrium in our daily life. When food is put in the refrigerator, the heat from the food is transferred into the air of the refrigerator. This process is continued until the temperature of the food is equal to the temperature of the air in the refrigerator, or when thermal equilibrium is reached. Thermometer is placed in contact with the patient's body. If both the body temperature of the patient and that of the mercury in the clinical thermometer have reached thermal equilibrium, then the temperature of the thermometer is the same as the body temperature. Hence, the reading of the thermometer shows the body temperature of the patient. Wonder why the swimming pool is too hot or too cold when you dip your toes in it? It is because your body is initially in thermal equilibrium with the air, which makes it either hotter or colder than the pool's water. If you dip your body into the water, after some time, you will notice that the water is not anymore too hot or too cold for you. It is because your body and the water have reached thermal equilibrium. The amount of heat absorbed or released by an object can be determined from the change of temperature because the temperature change, delta T, is directly proportional to the amount of heat absorbed, Q, given by the equation Q equals C delta T, where C is the heat capacity of the sample, usually in joules per degree Celsius. This quantity is the amount of energy needed to raise the temperature of an object by 1 degree Celsius. This quantity depends on the size. Of course, the larger the size, the higher the amount of energy required to raise its temperature by 1 degree Celsius. And it also depends on the composition. Objects with the same size but with different composition, for example, one is made from carbon and the other is made from copper, their specific heat capacity will differ. A variation of heat capacity that is more useful for calculations is the specific heat capacity of a substance. The heat capacity is directly proportional to the mass of the sample given by the equation C is equal to M times Cp, where Cp is the specific heat capacity usually in joules per gram per degree Celsius. The specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Moreover, the formula of heat could be modified to mCp delta T. Unlike the heat capacity, specific heat is independent of mass and volume because it describes how much heat must be added to a unit mass, meaning it is usually constant whatever the mass is. Unlike heat capacity, it has a varying value depending on the mass. Here's a table of specific heats for various substances in joules per gram per degree Celsius. The higher the specific heat, the higher amount of energy is needed to raise its temperature. Therefore, water needs higher amount of energy than olive oil to increase their corresponding temperatures. Let us apply the concept of a specific heat in phase change. For example, we would like to completely vaporize these ice cubes. To analyze what happens, we will discuss this with the help of the heating curve of water. In this plot, we can see what happens to the temperature when we continually add heat to the sample. Now, to be clear, we would like to calculate the amount of heat needed to completely vaporize the ice cubes. So, to do that, keep in mind the formula Q equals mCp delta T. The vaporization of ice starts by the addition of heat to bring its temperature to the melting temperature of water at 0 degrees Celsius. This temperature is also the freezing point of water. Temperature lower than this gives us a solid state sample. As you can see here, even though heat was added, the state of the sample is still solid because it didn't attain yet the melting temperature of water. To calculate the amount of heat needed to raise its temperature to the melting point, we use the formula Q equals mCp delta T. M is the mass of the ice, Cp is the specific heat capacity of ice given in the table, and delta T is the change in temperature, which is from a negative value to 0 degrees Celsius. Notice that delta T here will be positive. Therefore, Q will also be positive. Therefore, the ice cubes need to absorb this amount of heat to change its temperature. When it reaches its melting point, it will melt at constant temperature. At this point, both solid and liquid phases are present. Because it changes its phase at constant temperature, if we use the Q equals mCp delta T, we will be faced with a zero amount of heat, which will not make sense because we did add heat in order to melt it. Now, to calculate the amount of heat absorbed or released during phase change, we use this formula. In this case, it is the amount of the substance multiplied by the heat of fusion. Delta H subscript FUS. Melting is also known as fusion. Delta H fusion is given in the table. At this point, Q again is positive because heat is needed to break the forces holding the solid together to form liquid. While, if you want to do the opposite, which is to freeze the sample, you need the exactly same amount of heat to do it, but opposite in sign. Therefore, the Q for freezing is equal to the negative Q for melting. Therefore, we'll have a negative Q. And what does negative Q imply? It means that the amount of heat should be released to freeze the water. Now that the water has melted, next is we need to increase its temperature to its boiling point, 100 degrees Celsius. The amount of heat needed, since there is a change in temperature from 0 to 100 degrees Celsius, is Q equals mCp delta T. Assuming the mass of the sample is the same all throughout the process, M is the same as the amount of the ice. Cp will now be equal to 4.184 joules per gram per degree Celsius because the phase is now liquid. Then, delta T is 100 minus 0, implying again positive value of Q. If you add more heat, since it already reached its boiling point, the liquid will now start to boil at constant temperature, where both liquid and gas phases are present because phase change is happening. Here, Q again is calculated using the heat of vaporization. Again, resulting Q here is a positive value since heat needs to be absorbed to break forces holding the liquid substances to form gas. And again, if you want to reverse the process by condensing a vapor, same amount of heat is needed, but this time it should be released. Therefore, Q of condensation is equal to the negative Q of vaporization. The continuous addition of heat will eventually completely vaporize the water, so the temperature will also increase again. Since there is change in temperature, mCp delta T could be applied. It can be noticed that in this problem, we encountered again these two types of heat. The sensible heat, which is the heat associated with a change in temperature, and latent heat, which is the associated heat with the phase changes at constant temperature. Finally, to calculate the total amount of heat needed to completely vaporize the ice cubes, we just need to add the amount of the heat needed for the path water underwent. That is, Qt is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. To understand heat and specific heat, let us try to answer this problem. A layer of copper welded to the bottom of a skillet weighs 125 grams. How much heat is needed to raise the temperature of the copper layer from 25 degrees Celsius to 300 degrees Celsius? The specific heat capacity, Cp, of copper is 0.387 joules per gram per degree Celsius. The given values are M1 equals 125 grams, Cp of copper equals 0.387 joules per gram per degree Celsius, T1 equals 25 degrees Celsius, T2 equals 300 degrees Celsius, and we are required to calculate for the amount of heat needed to raise the temperature of copper. Since there is a change in temperature, we will use Q equals mCp delta T, where delta T is T2 minus T1. Substituting the values, 125 grams times 0.387 times 300 minus 25, we will get Q equals 13,303.13 joules. Since the answer is positive, this amount of heat should be absorbed. To understand heat and specific heat with phase change and thermal equilibrium, let us now try to answer this problem. If 90 grams of molten lead at 327.3 degrees Celsius is poured into a 300-gram casting form made of iron that is initially at 20 degrees Celsius, what is the final temperature of the system? Assume no energy is lost to the environment. So we have other information for lead. Its melting point is 327.3 degrees Celsius. Its latent heat of fusion is 2.45 times 10 to the 4 joules per kilogram. Its specific heat capacity is 128 joules per kilogram per degree Celsius, while for the iron, the specific heat capacity was given at 448 joules per kilogram per degree Celsius. Now, we are required to calculate the final temperature, which we represent here as T2. By thermal equilibrium, both lead and iron will have the same temperature, so there is only one final temperature, and that is T2. In this problem, since we have two objects or bodies, and it was stated that we need to assume there is no energy lost to the environment, that means whatever heat is gained by one object is lost by the other object. Then, it is better to start with Q lost plus Q gain equals 0. Depending on their initial temperature, one of the objects will gain heat while the other will lose it. Which do you think of the two will lose heat in the process? Is it the lead or is it the iron? Think. You are correct. It is the lead. Therefore, the other material, which is the iron, will gain heat lost by lead. Therefore, we can equate Q lost to Q of Pb, which in turn is equal to the sum of heats needed to change the temperature from 327.3 degrees Celsius to a lower temperature. Because Pb will lose heat, so it becomes colder. So its final temperature should be less than 327.3 degrees Celsius. And the heat associated when it solidifies. But how did we know it solidifies? Because in a given melting point, if lead acquires a temperature lower than that, it solidifies, as mentioned in the heating curve of water. Now, in terms of the variables given, heat lost due to change in temperature can be calculated as mass of lead multiplied by the specific heat of lead and the difference of the final temperature T2 and the initial temperature of lead. Then, for the heat associated with solidifying, the mass of lead should be multiplied to the negative value of heat of fusion, since fusion is from solid to liquid, and we want the heat from liquid to solid. Then, the heat gained by iron is only due to the change in temperature. So, it is equal to mass of iron times specific heat of iron times the difference of T2 and the initial temperature of iron. Then, substituting Q lost and Q gained to the first equation will give us this equation with T2 as the unknown. Substituting the given values and solving for T2 will get 59.37 degrees Celsius, which is lower than the initial temperature of lead and higher than the initial temperature of iron. Therefore, our answer is justified and correct. Congratulations for completing the discussion of Module 4.1.2. But we need to overcome one more challenge. Are you up for it? And these challenges are the SAQs, self-assessment questions. You may find a copy of these questions in the handouts provided by your instructors. Write your solutions in the Tomasian Honor Code in clean sheets of paper, scan or take clear photographs of your papers, and upload in the corresponding submission bins your instructors provided. This is the end of Module 4.1.2. If you have questions or clarifications regarding the topic and the SAQs, feel free to contact your respective instructors. Thank you for listening and have a great day.